we've got a solid ball, solid metal ball, and a hollow plastic ball. Solid metal ball. So right away we're thinking there's significant mass. Now we don't really know for sure, but I think the person who wrote this question wanted you to think more massive solid metal ball and a hollow plastic ball. Oh yeah, same external radius, so we know the solid one has got greater mass. And they're both dropped in a vacuum. When each has fallen 1 meter, they both have the same. They both have the same. Now it is a vacuum, so yeah. Yeah, oddly enough, isn't that weird? Now, why is that they have the same speed? Let's put a little explanation because that's even more important. What I would do is I would trot out, Newton's second law. You've seen it like that. So why is it that they both could have the same speed? Well, because they both have the same acceleration, which is, of course, 9.8 meters per second squared. Now, isn't that weird? Why would they have the same acceleration? Well, let's check it out. I'll show you it works. Now, acceleration is the ratio of the weight. Now, you might say, but that solid metal ball, its weight is so much bigger. Shouldn't it have a greater acceleration? Well, yeah, it's got a greater weight, but it's got a greater inertia as well. Look what happens to the m's. And this is what Newton told the world, that acceleration just doesn't, everybody thinks it's just the force. Well, he says acceleration comes from the force, which is directly related to force, true, but it's inversely related. And these factors cancel out. Because A equals F net over M. So the net force is just the weight, and the mass. So what Newton is telling us, no, what I'm saying is, what's the force? What is the force on a falling ball? It's when you got a falling ball, it's just mg. Oh, mg does not equal ma. Mg is the force on the. Say that again. What? Yeah. Well, I divided by m because I plugged it to Newton's formula. What's the net force on the ball? It's mg. What is the ball's mass? M. And I realized with them being on the top and the bottom, I can put mass is not a factor. It cancels out the top. Alrighty. So that's why if somebody asks you why, how could it be that a bowling ball would have the same acceleration as a lacrosse ball? A bowling ball has such big weight, and you'll say, yeah, it's got a bigger weight, but it's also got a bigger inertia or mass, and those two factors. And that's your explanation on that one over there. That might help you for tonight's homework. Number 2 is 700 Newton. By the way, this is a mistake. That inch. Could you change to meters? The person who wrote this meant to do meters. This is so simple. You've got this force, and you've got this distance, and you got this time, and power is W over T. I hope you remember that. But we don't have a W, but we do know we can find the work. F times D over T. And that big, go ahead. They're a little different, right? Yeah, you should look it out. We'll put it in our form. Most of them are pretty close, but that's a great idea. Great idea. So the answer in number 2, dig it out over here. 2 is 560. That's pretty basic. All right, railroad. Now let's talk about that handout we read. Railroad car colliding with another railroad car. Yeah, COM, right? We'll write a little note there. Something that comes from. Could you underline locked together? So the only thing that we're told is moving is the railroad car whose mass is m and his velocity is v. That's the only thing moving. That's the only thing moving. Because there's an inelastic collision, big M joins with little m, and you have a new velocity. People like to call that v prime. Well, now it's kind of a basic, good review of conservation of momentum. Oh, you know what? Could I just add something to the top? Conservation laws, right? Mechanical energy is not always conserved. Mechanical energy is not, but momentum is conserved. Remember that. There's going to be some point when they're going to want to know, do you know that momentum is always conserved? Now, I have a box, and I give it a real good push. Wait a second. The energy of the box, so when work is done on it by my system, I'm not expecting the energy at the beginning. However, was energy distributed? Yeah. The box is a bit hotter, so I say energy is always conserved. Now, but mechanical energy is not always conserved. You're going to drop a golf ball and it doesn't return to its original height. The golf ball got a little hotter. The floor got a little hotter. Yeah. One of those huge rules that momentum is always conserved. Always say, under what conditions is momentum always conserved? Well, now there's something called an elastic. You drop anyway. So, but the thing is, always say momentum's pleasure is always conserved. This one is so good because, could you write on the top vertical direction, y direction car with the water collecting? Yeah, it's rolling without horrific circle now. This door, people might be, isn't it? Well, it is, but with the mass, let me just get this right over here. because the mass of the car goes up, the velocity goes down to keep the conservation of. Do you get that idea? Yeah. Do you get that? Because the mass went up. How is the let's write this before x momentum before and after the same. X momentum before and after the same. So what Miss Doyle, I think, is thinking, as the mass goes up, the velocity must go down, because I was thinking that same thing this morning. I was thinking, I know that momentum is conserved in the y direction. So I don't know how that works. I was wondering. Now there is no y movement of the car. Oh, not even temporarily. With it weighing more, it's going to go up. Yeah, I was really pondering that this morning without having worked it out. I think there's movement of the water, maybe splashes up. I don't know really how it works in the y. I don't know the answer to that, but I know as the water comes down, the water has y momentum. So I wonder if it's go up, like the drips go down and maybe it bounces up or something. Yeah, I don't know the answer to that question. That's a tough question. Ms. Duca? Yeah, you can write P before. Well, if it's an explaining problem, so the conservation momentum, total x momentum, because the mass of the car is going up, the velocity must go down. Oh, the formula would be, but now it would be m, like if there were two things, it's like that. Now there could be one thing, and it's like this. It's a formula that kind of changes. If there's one thing in the beginning, then there's one momentum. This one is super easy. Units of, there are actually two incorrect answers for the unit of power. One's easy. First one, yeah. And actually, it's the second one. Mayor, getting it right. Getting it right. Very good. 1 and 2. 1 and 2. Choice C. Choice C. Okay, so let's look at this one over here. This one is so good. This is a really good question. You got these two objects, and we underline. That's what I like, because I want my information to stand out. And it's moving parallel to the x-axis. And I realize, in the very beginning, before there's a collision, these two things have only x momentum, because they're only moving the x direction. Then there's the fast one overtakes the slow one, which is the 0.1 kg. After the collision, the y component of the 0.2 object is per second. What's the y component of the other one? This is obviously a collision problem. I wouldn't say, well, it's true, before equals, it's not wrong that the total momentum before, well, I would think the principle here is that will help me do is the total momentum in the y direction before and after are the same. Now let's see what Sophie is thinking. How much y momentum did it have in the beginning? It had 0. Yeah, because it had no y momentum, because it wasn't moving in the y direction. So, helpful thing that she's thinking about. So the total y momentum before is 0. So I might say py equals py prime, py before and after. Now, the 0.2 kg, it had a speed of, let's see, 1 meters per second, and plus the 0.1 kg, and I don't know its velocity, so I'll call it prime. But I do know they add up to 0. Yeah. Well, then I can send one on the other side, like you do in math class and algebra problems. Send one of them. Maybe you can set. This is just what, right? You got that? Now, why did she say downward? Because in getting a negative number, when we establish up as positive, be down. That's how it works. Then there's a kick, and they want to know impulse. And impulse is F times T. But that's not really helpful, because I have neither F nor T. But I do. Anybody remember what else it equals? Oh, beautiful. Oh. So when I give an impulse to something, it's a force multiplied by time. And if I'm a good baseball player, I give a big force and a good follow through. That's contact time. And if you're a baseball player or a tennis player, why do you want that? Because it'll really give you a good change in momentum. Now, I got an M and I got a V, but what about that just M delta? And so the answer, well, it would actually be VF plus, the average is VF. That's for average. That's like D is V average times like that. Okay, so the answer to this one actually is what, 4.5? Did somebody work it out? The answer key actually had the wrong answer. Unless I'm looking, I think, I'm looking at the wrong thing. The answer is, sorry about that, C. This is C. Yep. What? Okay, C. Okay, so here's a swinging pendulum. There's a mention of potential energy, so clearly this is an energy question. where the let's go over what she's thinking. She's thinking, well, this is at half the height, isn't it? Right there. If you look at the picture, it's half the height. So it's if I had to explain this, I would say, well, at that point, it's half. So it's half the potential. And if you have half PE, well, then you have half, right? Because the energy doesn't change. Half the PE, half the PE gives you half the. Hey, let's add to this so we have more notes. Ready? This is where the PE is at the maximum here, and at the bottom. Whoops, at the bottom KE max, and the speed of the ball at 2. The speed of the ball at 2, which is at the bottom. So now that alone wouldn't be enough. I'm thinking because it's kinetic energy, but right, mg. We are on number. We already did where would the kinetic energy right here 3, Roman numeral 3. So this is conservation of energy. We've got no energy loss in this pendulum, of course. I know it's an ideal situation, but that's what they're presenting here. There's no air resistance, so that tells me that it's not going to lose any energy. So the m's cancel out, but where do we get the h? Well, that's over here. If that's the halfway mark, then yeah, you need the this is PE max. Yeah, thank you for that. PE max. Yeah, thank you for that addition. The KE max equals the PE max. The bottom is KE max. That equals the PE max. So it's 1/2 v squared equals GH. 1/2 v squared equals G. Multiply both sides by radical 2. Multiply both sides by 2. Oh, look at the picture. Look at that picture, that Roman numeral 3. Doesn't that look like, well, those are 2 equal segments. We have to kind of eyeball it. If that's 0.5, the next segment up would also height that max. Oh, but we're talking about that. We're saying KE. It's KE max. Good. Some good review questions here. Now here you have the choices are gone. On my sheet, are they gone on your sheet as well? No biggie. So we don't need any. But this is a great question. You've got an explosion, a stationary object, and it goes into 3 pieces. Both of them are NV, and then this piece over here is 3M. So it's got 3M and some V. So good. Now, what do we know about what physics are we going to use on this? We've got right. This is a momentum. In fact, the conservation momentum. Write down the total momentum before the explosion is 0. Well, true that these 2 momenta have to equal this one momentum. But then you might say, well, how am I going to add up mv plus mv? It's not 2mv. What do we use to add up 2 perpendicular vectors? Good, right? P. So why? Because it's 90 degrees. And so now to add them up vectorially, so then it just becomes m squared v squared plus m squared v squared has to equal 3m v prime. Because I don't know what the v prime is. So now I have to, I got to take the square root. That's what the Pythagorean theorem says. So this is mv v prime. 2mv prime. Cancel out. And divide both sides by 2/3. I'm sorry, 2/3 v. Excuse me. Oh wait, no, that's a mistake. Oh, I'm sorry, my bad. This should have been. This is radical. I'm sorry, I did the math wrong. So what happens is, let me clean this up and fix this. Just give me a second. I did the math. This under the radical becomes 2m squared v squared, right? So my math was wrong. So when you add up these 2 things in the radical, it becomes 2m squared v squared. So radical 2 comes out. Let me see if I can get my thing going here. Okay, so underneath the radical is 2m squared v squared, 3m v prime. Sorry about that. So it's radical 2, m times v equals 3m. So bye-bye, and you divide both sides by 3, so it's radical 3. With an explosion of a stationary object before and after. So then the 2 pieces going this way have to be equal but opposite. Is going that way. And oh, one more thing, because you can't see the answer choices. I knew that the pieces go this way because it has to have the same y before and after. Could you do that? Like show that the thing will go, it'll have the same x and the same y. That's why it's going to go in exactly that direction. Good one. It's a plot of f versus d, and the first part's super simple because they ask you for the acceleration. If you've got force and a mass given to you, I hope you know what to think of when you think of force, mass, and acceleration. Juliana, what am I talking about? Write down the equation. Tell it the force, mass. Right. Sum of the forces equal ma. So I'm going to put that down right away. If I have to do an extend response, I'll get some points with that. Now at 6 meters, the force was 4. You told the masses, and you'll have something. You always get kind of a divide both sides by 0.2, not squared. We substitute with units, and we 20 without the. Let's see, without the decimal 4 had. Now the next would be the time taken for the object to be displaced 12 meters. I don't know how to do this. This is my exact approach. What the heck do I do here? Let's see. I found from before the acceleration is 20. Let me just write down what I got. Oh, the time is the unknown. Oh, it says it starts from rest. Oh, now I know what to do. What do I do, Miss Mayer? Oh man, you're sharp without the DC. You're very sharp. So D equals VIT plus 1/2 AT squared. D equals VIT plus 1/2 AT squared, which also simplifies it just this. And you get, I believe you get 1.1 seconds. Technically, the answer should be good. Doyle? Okay, good, yes. Next question is much more interesting. 100% chance on the test, you're given a plot and asked to do something like this. The work. Well, I go, this is actually kind of simple. Work is just F time basic. I wish they would have asked, how about how much work was done the whole? Let's add that question. Now, it's really easy to get the work because it's just F times D, so it's times the distance of 12. This is too simple for like an AP question. This is 48 joules or Newton meters. I would have loved if they asked you the whole time, what would you do for the work for the whole time? Let's write this, yeah, right. Let's write that down. Work equals area. That's more like an AP question under F versus D plot. They're gonna try about 5 times how to get values from a plot by using. Now, the calc, when the shapes aren't easy like this, don't worry, you don't have to use any calculus on this calculus, but it gets shaped, the trapezoid. So,
Me and Greenhorn have B.
you gonna take AP calculus here, though?
I didn't. I don't remember how I did on volumes. I like it.